tell me why men can't jump. Now let's go ahead and look at that same data set, but instead of looking at temperature, we're going to look at humidity, which is going to make it a little bit harder. And once again, I've already got the code mostly written up, partly because I figured you don't want to watch how many times I can misspell that stupid word, humidity. There's a histogram. It looks like humidity is mostly low in the 0 to 50, certainly 0 to 100 range. And if I had to predict the mean, I would say I'm 95% confidence between 15 and 16.5, which is pretty low humidity. These are the fixes that we did when we looked at temperature, so I know I'm going to need them. Let's look at the relationship with humidity. See these high outliers here? A lot of humidity temperatures are very low, with occasionally really high. It is possible to have humidity over 100%. I think pure water is like 1,000% or something, so 400%, I don't know if that's realistic. It's made up data. Just follow along, okay? Once again, high outliers. Every single one of these plots has these extremely high outliers in the y direction. So that should be a hint that what we really need here is a log on humidity. Let's look at these same plots, but with humidity logged. And we see great improvement in the outliers. It still does seem a little skewed, and it will. Also notice these stripe patterns that happen here at the bottom of the graph. That happens because when you logged it, some of the small numbers had, for example, 0.37, and that seems like lots of decimals. But if you had a large number like 12.37, that's 4 decimals of accuracy. So what we're seeing here is an artifact of logging a variable that doesn't have consistent number of digits, because we have a certain number of decimal places, and for a larger number that means more digits before the decimal and after the decimal. So these are nicely spread out, but here we see these lines. So we're not going to worry about these lines. That's just an artifact of the rounding and the logs. But let's look at each of these graphs. Do we see anything interesting? Here on Win, seeing some outliers, so maybe a log there. This one, there is definitely an interaction happening, okay? Something between altitude and, it looks like a 2-dimensional variable, so we'll keep that in mind. And if we had to pick a variable that only has 2 options, animal behavior is a good pick. And sure enough, we can see that it is definitely split by animal behavior, typical versus normal. So we're going to put that in. These, I don't see much. This one, okay, snow melt, maybe a log. I think that's what we had on the last model, and it turned out to be significant. These ones, it's really hard to see much pattern. Now, this one, funding, I really felt like maybe there was some curvature going on here. I think at this point I didn't put it in, if I remember what I did earlier this morning. So let's do the model where we didn't log humidity. Would we see a clue that we have missed something big? Here's what the residual plots look like. Not okay. Big swoop, high outliers, definite patterns. We're missing something. And how do we know for sure that it is the log on y and not log on some of the other variables? Well, here's what the residuals look like. According to air pressure, this all looks fine, but huge residuals in the y direction. And so this tells us perhaps a log of y is what would fix it. So it would make sense that we would try the next fit, having the log, and improved. Okay, not great. There's a horn shape, there's still some swooping, but certainly better than what we were looking at. So now let's go through the residuals for each of these. That one's looking okay, looking good. This one, I thought I should log it and actually typed in log this, and then I looked and saw that it was already logged. So yeah, now here we have a problem. Is this curvature? Would a log fix it? So we've got to work on altitude a little bit. Here's clouds. Snow melt again. I thought maybe a log, but it already is logged. Mathematicians are saying, go ahead and log the log. That's doable. Yes, it's doable. Does it make sense? No. And if you want to go ahead and do silly things like logging a log, you're welcome to. I am not myself. So, okay, and animal behavior, you can see small variability, larger variability. So that's interesting. So for this one, what are we going to do? We're going to go ahead and put in an altitude squared, see if we can find why altitude is curving. And this, I don't know, it doesn't seem like it's really fixed a lot. This is the one, did altitude get fixed? No. So we still need to try to play with that, see if we can get some good things. And here's polar vortex. Do you see a pattern here? I see a band in the middle and then a larger band on the outside, so maybe there's something going on here. And funding, I'm still thinking maybe I see some curvature. I could be making it up, but I think it's worth looking into. And animal behavior, still we see super skinny box plot here and a fatter box plot there. So I was thinking perhaps there could be some other interaction with animal behavior. For example, we looked at polar vortex being funny. Here's polar vortex colored by animal behavior. Remember how I said there was a band in the middle? That's the skinny animal behavior. The wider one must be unusual because unusual was the wider band. So unusual and typical. But is there an interaction here? Does polar vortex change depending on which animal behavior we're talking about? And the answer is no. It seems to go straight across no matter what it is. So I said, let's look at altitude. We can see the triangle within the other triangle. But what needs to happen here? Is it curving? Is it logging? I'm not really sure. So I was going to erase this part of code. This is actually what I did is I went through and said, okay, let's start with each of these. Let's do 3 and look at that. Let's do 4 and look at that. I was just hunting around. Eventually I started doing, well, I made this variable I to help keep track of things. And then I just went through plot after plot looking at how they related to animal behavior, thinking that I would find some magic plot that needed to be fixed. And in the end, no, I really couldn't find any particular plot. It's still altitude that's looking funny, right? Here's the altitude one. So at this point I said, okay, let's try altitude squared times animal behavior. Let's try log altitude and times animal behavior. Just trying to see if there's something that would give us a good match here. And I realize this is totally fishing. I'm running the risk of finding patterns where there's really nothing, but I'm looking for something that'll help give me hints. And has this straightened out a little bit? I still don't like the tails here. There's still this fanning horn type shape. So the residuals aren't exactly making me happy. And as I go through each of these, I don't see anything there I can fix. Nothing there, nothing there. Here's wind speed, altitude. Yeah, no, still not fixed. And I don't know what other ideas there could be. So it might be that I'm going to have to accept that I can't get the perfect residuals that I want. And that's very realistic. Sometimes in real life, especially if it's real data, you don't get beautiful looking residuals. You've kind of got to accept that. It may be there is no perfect model. Instead, our goal is to come up with the best model we can using the tools that we have from this class. And right now, I think what I have is about the best model I could expect a student using these kind of tools could do. And if you want to talk about more ways to handle error structures and variances, the multivariate class goes into more types of models and how they're analyzed and options that you can do. But so far, I'm going to say this is going to be the best model that I can get. So let's look at our summary. And I'm looking for variables that can be taken out, and it looks like there are some. Snowmelt here is pretty high with a p-value of 0.7. So let's try taking that out and see what we think. After that, it looks like I said system. Yeah, well, look at those big p-values. And system's a categorical variable. It's pretty confusing. Now, looking at the rest of these, my p-values are dropped into the 0.5 range, right? There's for log wind speed. But I'm looking at some of these hugely complicated things like altitude squared times animal behavior. And with a 0.3 p-value, this might be a good pick to take out next. There's nothing that's drastically worse in p-value, and it is a very complicated variable. And look, that fixed a lot of p-values. Now log wind speed. And that's good because I have wind speed. I shouldn't need wind speed here and log wind speed here. It should be one or the other. So since log wind speed has a big p-value, let's take it out. That's theoretically better and helps simplify the model. Now we're looking for big p-value. Clouds here is at 0.45. Also percent recorded is at 0.47. I think percent recorded is the one I picked off next, sure enough. So after each of those, we're looking at ground level, which is here at a 0.15. And this is called backwards regression. We fished around for so many patterns. It's going to make sense that we found some junk that doesn't need to be in there. Air pressure is a 0.22. So let's cut that out. And polar vortex might be the last one, 0.12, and then everything would be significant. Now, at this point, everything is significant, but I have a little problem with altitude. I have altitude, altitude squared, and log altitude. It doesn't make sense theoretically for it to be altitude squared and log altitude. It should be one or the other. And that worries me. I'm hoping maybe if I get some of these last ones out. See, that guy's only barely not significant. If we're going to stick to our strict rule of 0.05, then I'm going to take out pressure change. Plus, it'll make my model a little smaller. So we'll be strict. And log altitude is still significant along with altitude squared. That still worries me. So where is funding cubed? Funding cubed 0.05, barely not significant. We could argue that we want these to stay in here because they're almost significant. If this was an exploratory study where we're looking for things that we can apply for grants to study more, we might leave funding cubed in there to say, we need to study this. And finding cubic patterns is hard, so give us more money so that we can get more data. Because funding cubed gets cut out, funding squared now looks terrible, so we ended up with no curvature on funding. If you remember earlier, I warned you I might be seeing patterns where there was nothing, and if there was a pattern there, it just wasn't quite enough to really show up. Everything's still significant, and I still have log altitude and altitude squared. That makes me uncomfortable. So this part of the code, I tried to decide which direction should I go, and I realized I could, real quick, show you both directions. If I want to leave in log altitude with altitude, because I would say that that helps the predictions, here's the graph I would make. It looks like that. Does that match the original graph of the distribution? Yes. Notice the scale is different, and that's because I have not included any of the other variables. This prediction right here is only altitude and animal, which has that interaction. But I didn't include, for example, radiation, funding, and wind speed, and having those variables in would have changed this scale, made it look better. Also, another really important thing right here, notice that guy? I actually forgot him for like 10 minutes, and it wasn't making the picture I knew it should make, because it's supposed to make a picture like this. And I finally remembered, humidity got logged. So if I don't unlog it, then what I'm plotting isn't the picture of the actual humidity, it's the picture of the log humidity, which nobody really understands what log humidity is. So for predicting humidity, you want to do e to the power of e because I did log base e. If I had done log base 10, then I would have wanted to do 10 to the power of, but that's not what I did, so there's your e. Now, as much fun as that was, and you are perfectly allowed to do that, and I will accept it, I decided to take it out because it really shouldn't have log of altitude and altitude squared. So I'm going to justify that log of altitude really doesn't belong there. It's a pattern that we're finding just because we kept fishing for patterns. So looking at the p-values now, everything is still good. Without it, how much of a difference did it make? Well, we'll find that out in just a minute. Let's first plot this new graph. There is the graph without log humidity. Here was the graph with log humidity. So can I delete this graph in the middle? Okay, there's with log, without log. I hope that the visualization on this video is good enough. You can see there is ever so slightly a bend right here that shifts and changes. And according to the data, it really should shift and change right there. Is it enough that I'm going to say I want to leave in log and altitude squared? And I'm going to argue no. So I want this to be my final model. It doesn't have log of altitude. So there's all my coefficients. This command, when I had it on full screen, I have to shrink it down for the video, so it's frustrating because it doesn't all fit, but it fit and looked all nice. Incidentally, for wind speed, because in my model I have log y depends on wind speed, I have to do a little bit of math to be able to interpret the slope on wind speed. Same with altitude, radiation, funding. And over here with snowmelt, that's a log interpretation, so I'll have to do that one a little different. And then, of course, altitude, I'm going to want to do this picture. So I went ahead and did all these guys down here. Wind speed, there's the coefficient. So if I take e to the wind speed, I'm multiplying my response by 0.9. How much does that change the response? Well, if you time something by 90%, that's basically a 10% drop. So it's 0.09, so a 9.5% drop in the response. Radiation is an 18% increase. Why increase? Well, you can see this one has a negative slope, this one has a positive slope, so of course it's going to be increasing. How much? 18%. Funding is negative, so it's going to be decreasing. How much is it decreasing? Well, it's 96% less each time, which is a almost 4, well, it was slightly more than 96. So it's a 3.39% drop. And smog and snow melt, and I did all these. And then I wanted to look at my residuals. Look at that. We still ended up with the horn. Now, we said this was the best we could do, but can you at least tell the client why these residuals are acting funny? And the key to that for me was altitude. Low levels of altitude have lots of variability. High levels of altitude, very low amount of variability. And as much as we tried a whole bunch of different things to see if we could fix that, we just couldn't find something to fix it. So it looks like altitude really does have higher variability on the low end and a small amount of variability as you get to higher altitudes. So what am I going to tell the client? Well, let's start by talking about the response. Here's what it looks like. Here's where the average is with 95% confidence. Just kind of talking about here's the types of humidity that are typical. Now, what affects humidity? Well, we've got a model, but this model is going to need a log humidity. Why? Because I saw these huge outliers, and once I took it out, I fixed it. And yes, there are streaks. I think the client deserves to say I didn't not notice them, but those streaks are part of the rounding issues when you're logging data that has a consistent decimal point. So I'm not going to be concerned by these. If I had dragged out more decimals, like 30 decimal points, then these would all space out nice and even the way we would hope they'd look like. And so then I have a little sentence talking about why did I log snowmelt and why did I do an interaction? What was it that I was seeing that made me want to do these things? Which helps the client to understand what it is you're doing and why. It also helps the teacher who has to grade you on whether you know what it is that you have to look for. So we look at our residual plots. Yes, there's still a horn shape, and that's concerning. Now the stripes necessarily aren't. That's a logging issue with the rounding. But that non-constant variance comes from the altitude. Low levels of altitude just have high levels of variability, and vice versa for the low end. Now, if we were in a higher level stat class, we might talk about how you would change the way you do the prediction based on the altitude level, because here your prediction can be very skinny with a small interval. Here your prediction would need to have a large interval. For this class, we're not going there, partly just because there's not time to go into all those details. Just understand and recognize that you have non-constant variance and where it's coming from. Now, I'm also going to mention that I tried a lot of other interactions. I tried a bunch of other logs and higher polynomials. I didn't include it in this video because I spent a little bit of time fishing around trying to see if I could make things look better. In the end, none of those worked out, but it helps the client know that you did search for the right way to do things and you've decided this is the best model. It also helps the teacher to know that you didn't forget to try to check some things. So here's my prediction equation. It's hard to see because it's e to a power. Look, there, we'll zoom in. So there's my whole prediction equation. And for animal behavior, I had to change the intercept. I also had to change the slope on altitude, and I had to change the slope on altitude squared. But there's prediction equations. I think a client would like seeing that. Now, for explaining the effect of those linear x terms, remember that y got logged. So increase of x leads to a percentage increase or drop in y, except for snowmelt. Snowmelt was also logged. So there's our log-log example. As it increases by 5%, then humidity is expected to drop, and this was really a small number. It was 0.000501. So if you turn that into a decimal, which moves the decimal point over, it's 0.05%, so a really tiny effect, but there's enough data to show that effect really is there. Here's my interaction, which you should feel comfortable with because we've done lots of these, and then something to talk about what it really means. The client wanted to know how to predict humidity. Well, the most humid days happen when all these variables are in just the right amounts, and how do you get those right amounts? I thought in the last video we decided you lived on a nuclear power station on top of a mountain. So there you go. I still don't really know how funding seems to affect the weather. It sounds a little fishy, like an X-Men movie or something, but this is very complex. It's about as complex as your final project. So let's go through a couple of homeworks. One of them is going to be probably the hardest homework you've faced yet, and then you'll do something that's going to feel a little bit like this weather data.